Let's talk about the ultimate rulebook. Not for a game, not for a country, but for the entire universe. And you know what's wild? It's surprisingly short. There are really just 4 fundamental rules that govern everything.
Okay, just look at this. That incredible nebula, all the stars inside it, the planets we can't even see, even the device you're watching this on, and the very atoms that make you, well, you, all of it. And I mean all of it, operates according to just 4 fundamental forces. They're basically the architects of reality.
And here they are, the big 4. Gravity, the weak nuclear force, electromagnetism, and the strong nuclear force. Every single thing that happens in the cosmos, from a star-going supernova to a thought firing across your brain, it's all because of these 4 forces playing their part.
So how do these forces stack up against each other? I mean, are they all created equal? Not even close. To really get a handle on them, we gotta put them in their place. So let's rank them by strength, from the weakest to the absolute strongest. And I think the results are gonna surprise you.
So, coming in at the bottom of the list with a relative strength that we're just going to call 1 is gravity. Yep, the force that holds entire galaxies together is pound for pound the wimpiest of them all. We're just using it as our starting point, our baseline.
All right, next up, the weak force. And let me tell you, weak is a terrible name for it because it is a staggering 1 trillion times stronger than gravity. To put that in perspective, if gravity is like a single ant lifting a breadcrumb, the weak force is like the entire planet Earth lifting a mountain. This is the force that handles things like radioactive decay, letting particles literally change their identity.
Okay, now we are really stepping into the heavyweight division, electromagnetism. This one clocks in at 10 to the power of 35 times stronger than gravity. This is the force behind light, electricity, magnets, pretty much all of chemistry, and by extension, all of biology. It's a monster.
And finally, the undisputed champion, the strongest force in the known universe, the strong nuclear force. It's about 100 times more powerful than even electromagnetism. And what's its job? Oh, nothing much, just binding the very heart of atoms together. Without it, nothing, and I mean nothing you see around you, could exist at all.
So here's a quick summary of the whole shebang. You can see the strength rankings we just talked about, right? But check out that range column. This is fascinating. Gravity and electromagnetism can reach across the entire universe. Their range is infinite. But the strong and weak forces, they only work over these impossibly tiny subatomic distances. That difference in reach is just as important as their strength. And see that other column? Interaction particles? Each force has its own special particle, and that's a clue that we're getting into some really deep territory.
So we've seen the cosmic pecking order, but which of these forces actually has the biggest impact on your day-to-day life? Well, sure, gravity is keeping your feet on the floor, but the real powerhouse, the force that literally shapes the world you interact with every second, that's electromagnetism.
Let's break this down. So we know it's the second strongest and has an infinite range, just like gravity. But here is the secret sauce, the thing that makes it so special. It has 2 sides, a positive and a negative. It acts on this property we call charge, and this 2-sided nature, well, it changes absolutely everything.
And here's the bottom line. Gravity only does one thing. It pulls. It's always attractive. But electromagnetism, it can push and pull. Opposite charges attract each other and like charges repel. It's this constant dance of push and pull that allows stable atoms to form, that lets molecules link together, and at the end of the day, it's what makes chemistry and even life itself possible.
This force is just so central to our lives. But how did we even figure any of this out? It wasn't overnight, I'll tell you that. The story is this amazing journey that took thousands of years, starting with just a curious little observation and ending with some of the most powerful equations in history.
So it all started way back around 500 BC. The ancient Greeks noticed that if you rubbed a piece of amber, it would suddenly attract little bits of fluff. Now the Greek word for amber was electron. Sound familiar? Okay, now fast forward over 2,000 years to 1786. A guy named Charles Augustin de Coulomb actually measures this force with incredible precision. And then the grand finale, 1873. James Clerk Maxwell takes all these separate ideas about electricity and magnetism and weaves them together into one single, breathtakingly beautiful theory.
And this image right here shows you the heart of it all. It really just comes down to the interaction between 2 little charges. We can call them Q1 and Q2. And the law that describes how they talk to each other across that distance is it's beautifully simple.
It's called Coulomb's law. And put simply, it just means the bigger the charges, the stronger the force.
But the farther apart they get, the weaker the force becomes, and it gets weaker fast. Think of it like a tiny candle flame. If you double your distance from it, the light isn't half as bright, it's only a quarter as bright. The electric force drops off in exactly the same way.
And, the power of this single idea is it's staggering. As MIT physicist Scott Hughes said, it's kind of amazing to think that almost everything we understand about electromagnetism, from the circuits in your phone to the light traveling from the sun, it can all be derived from this one single assumption. It's an unbelievably powerful foundation to build on.
Okay, so we've done a deep dive on the force that really builds our world, but now it's time to zoom back out. Let's put it back in context with the other three, because the ultimate dream, the holy grail of physics, is to figure out how all these pieces actually fit together.
And here is the grand challenge laid bare. On one side, you've got the completely bizarre quantum world of the strong force, this chaotic, messy dance of particles being thrown back and forth. And on the other side, you've got gravity, which we describe as this elegant, smooth bending of space-time itself. I mean, these two pictures of reality could not be more different. So how in the world do you unite them?
One of the biggest ideas in modern physics is that forces aren't some kind of spooky action at a distance. They're actually transmitted by tiny little messenger particles. Electromagnetism has the photon, the particle of light, the strong force has the gluon, the weak force has its W and Z bosons, and get this, we found all of them. But what about gravity? Well, its messenger particle, the so-called graviton, is still a ghost. We've never found it. And gravity just stubbornly refuses to fit into that neat quantum picture.
Which leaves us right here, with the biggest, most profound question in all of science. Are these four forces really four separate rules, or are they just different faces of a single, deeper, unified force? The hunt for that theory of everything, that one single, elegant rule to describe all of reality, that is the ultimate quest, and it's a story that is very much still being written.